So far we have studied various instabilities which takes you to turbulence. Then I did energy transfers in the last class. Now I will discuss how to simulate, simulate a flow, hydrodynamic flow, as well as compute the energy transfers. So, mode to mode transfer or energy flux. Mode to mode formula you have it, so I will not describe it in simulation, but how to compute fluxes which are very critical, and after that I will go into Kolmogorov theory. Okay, so that will be tomorrow. Okay, so let us start. So today is simulation using spectral method. So I want to say a few words. So there are many methods, finite difference, finite volume, finite elements, vortex method, but in this course we will focus on spectral. Okay, one thing is I work on this and I like this, and it has advantages as well as disadvantages. So one advantage of this scheme is that it captures scale by scale flows, or flows at different scales, large scale, small scale, small scale. I think I did mention this before. So there are various wavelengths, so I am going to basically Fourier transform the flow. So that will give me amplitude at different scales, like you already done in the homework and projects. So it captures amplitude of the flow at different scales, which is not possible with finite difference. You will have to work as a post processing after you get the data. There every point which is equispaced, or maybe there is some points are close by, but you find the velocity at different points at a given scale. Okay. If somebody asks you what is a flow structure at large scale in finite difference scheme, you will have to take the data and then do the transforms, Fourier transforms, or something called POD, proper orthogonal decomposition, and this PCA, principal component analysis. All that is done on top of the data, but spectral gives you from the output itself, because lowest Fourier mode, the amplitude is the large scale structure. Okay. So and also various transfers at different scales. I described in terms of Fourier. There is a way to also describe in terms of real space, which we will do it bit later. But Fourier space gives a very good description of how energy is flowing from one Fourier mode to another Fourier mode, one scale to other scale, and that is why it is very useful. Disadvantage of this method is that it kind of requires very idealized geometry. Fourier transform means periodic box. I can work with the no slip box or free slip box, so boxes which are free slip at the top and bottom walls. We can do it with the spectral. Other things like no slip, or especially tube or turbines, this is very difficult to do in spectral. In fact, it is impossible for some flows. So many engineering flows we do not go for this method. Alright, so with this background let us start how to solve our equations in spectral space. So let us take only hydro, okay, right now hydro, but I will, well, it is very easy to generalize it to convection or MHD, no problem. So let us just work with hydrodynamic flows. So this equation I have done it many times. So this is in Fourier space. Okay. So this is my amplitude of Fourier mode k, Fourier wave number k. I means component is tensor notation, I is x, y, z. Now this is a viscous term, right, nu k squared. This is a pressure. So grad p becomes I k I p, and this is a nonlinear term. I am not writing expanded version, but I am writing like this for a reason. So we will compute the nonlinear term by some trick, which I will tell you a bit later. Okay. So everybody is happy with this, the same equation which I did before. We can add external force if you like, which I think I do not have it here. No, I have a force. No, I am sorry, so this should not be there, right. So this external force, this repeated twice. Now, a divergence free condition, that is k dot u, which is straightforward, k I u I k. So, this is a constraint, this is not a equation, this is not a evolving equation, it does not help you in evolving the velocity field, but it is a constraint on u. Okay. So, we will have to satisfy, well, basically pressure will be computed using this condition which I told you before. So, this condition is basically helping us compute pressure. So, pressure in mathematics language is Lagrange multiplier, in fact. Multiplier. So, this is a constraint and this constraint is used to compute pressure. So, this is what I write pressure. How do I get? So, this is, so multiply by k I. Okay. So, this left hand becomes 0 and this gives you k squared, and these two terms well need not be 0, force as well as the nonlinear term. So, n, am I making a sign error? I made a sign error. So, this should be minus sign. There are too many typos. You know why? Because my definition of nonlinear term is u dot grad u. N vector is u dot grad u. When I take it to the right hand side, there must be a minus sign. Okay. So, the minus sign is here. So, minus, so that is why n minus f. So, I take it to the left, so that becomes n minus f and divide by k squared and I. Okay. So, this pressure, this we have done it before, but you must remember that sometimes you should not ignore pressure, force. Force may be divergence free, the force may have divergence, k I f I need not be 0, and I put a notation this for our consistency. I put a subscript u, that means this force on u. There could be force on other fields like magnetic field or velocity field or temperature field. So, then it becomes f b or f theta. Okay. So, this is a notation. So, there are few typos here. Okay. So, what is the method? It is very straightforward. So, let us just go back a bit once more. So, get rid of this one. So, this is a set of ordinary differential equations. But this is not a PDE, I already converted to ODEs, and how many ODEs I got? Equal to number of Fourier modes or Fourier wave numbers. So, whatever k, every k has a ODE. Okay. And what are the terms? So, I am basically writing as d by dt of u I of k. So, it has 3 components, not all of them are independent. If I use Cray-Haring, then I have 2 which are independent, but we solve using Cartesian. Okay. The reason is Cray-Haring, the components keep changing for different cases. So, you have to keep track of it. So, nonlinear term, computing nonlinear term with, you saw that, I mean Cray-Haring, if you are single triad, great, but if you have more than one triad, then you have to do a lot of work. With Cartesian is not, I mean, it's straightforward. So, ui, so right hand side will have this term, this term, this term, as well as the viscous term which goes to the right. So, how do we solve this stuff? The method is called collocation method, which I will not differentiate among other methods. So, I have my box. So, I am going to put some of this stuff. My box is 2 pi by 2 pi by 2 pi. We can do it for arbitrary box, but for simplicity I am choosing is 2 pi. The reason why it is 2 pi is my wave number k is a vector, but let us say I am looking at kx, which will be 2 pi k by L x. Okay. So, k bar is a integer. Now, if box is 2 pi, then kx equal to k bar. So, kx becomes an integer, which is convenient, we do not need to multiply by a factor. But in our code, which is the lab code, we could put arbitrary Lx, so this becomes a prefactor. Okay. But for this box, like we keep it simple, keep our life simple, we just use 2 pi box. In real space, so we basically we have a 3D box, and we discretize like finite difference scheme, discretize the whole space into fine mesh. So along x direction is nx, along ny y is ny, along z is nz. Along each direction, since it is Fourier decomposition, is minus ni by 2 into ni by 2, right. Fourier wave number takes both negative and positive values. Now we probably need to be slightly more careful. Not both ends are not included. So right end is included, not left end. So what I mean is, it 0 is here, nx by 2 is here, which is included, but n minus nx by 2 is not included. So the left hand side is just 2 plus 1. So you can see that there are how many points are included in this? Minus nx by 2 plus 1 to nx by 2. This is nx points. If I had put minus nx by 2, then it becomes nx plus 1, then there is a problem. So Fourier transform is a linear transformation, right. So given ux in 1D, I get u of k, or vice versa, no? And if any variable becomes more, then I will not be able to do unique, I will not be able to get unique solution. This is basically a matrix, if you notice it. If I just write for 1D, okay. So 1D is u0, u1, u2 da 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 is equal to matrix Fourier u0 Fourier, okay. So let us go Fourier u1 like that, and this matrix composed of e to the power I k x. So that is a transformation, and so we can't have, so this matrix must be nx by n by n, and that is non determinant not equal to 0, right, for unique solution and invertible. So yeah, we need it towards later today, later part of today's lecture. We need to know this one, that I keep only from here to there, and there is a reality condition which I am going to come to it in a minute. So this reality condition, so this is has to be satisfied because velocity field is real. As a result, in 3D box, actually I can illustrate in 2D very easily, but in 3D it requires bit of visualization. So let us work in 2D. So we have this box. So this is x axis, y axis. So this is nx by 2, right, and this is ny by 2. This is minus ny by 2, and this is minus nx by 2. But this line is not included, huh? And this line is also not included. But in fact, we don't. So reality condition, what does it mean? If you have some wave vector here, kx ky, then in the negative direction we also have a vector. So if this is u of k vector, then this u star of k. So I don't need to save. In fact, I don't want to save that part. So if there is any error, then reality condition will be violated. Time stepping always will have error. So when I time step, this number and this number may not be complex conjugate after time stepping. So best is to get rid of this. So you simply don't save this. Okay. So you save only half the modes. In 3D kz greater than equal to 0, in 2D only ky greater than equal to 0. There is only one catch. The catch is the following. So, I am going to not keep anything below the x axis, but I have to keep the x axis. Is that correct? Because there are the 0 is a very important point, or shunyam is really important. So, you have to worry about 0. But if you keep this part, then what is the complex conjugate minus k for this wave number? It is on the line itself. So, if this is vector k, this is vector minus k, and I want to keep the full line. It is too much labor if you keep half the line. Ideally, we would like to cut it like that. Then you do not need to worry about this half. But if you keep the full line, which is the convention, then you have to make sure that this point here, the velocity field is complex conjugate of this. So, this condition has to be satisfied. If this is alpha, then this must be alpha star. Okay. So, this reality condition we need to make sure that it is working, otherwise your code will have problems. Okay. In 3D, simple generalization. So, anyway, these are some rules we need to keep in mind, and if you are doing it properly, then it is quite easy. Okay, initial condition. So, this is the initial value problem. So, given the initial velocity field u, k at all wave numbers at time t equal to 0. Okay. So, at t equal to 0, whatever. So, I am working with the initial condition in spectral space or Fourier space. If you are given in real space, you have to convert into Fourier space. Okay. So, this is my initial condition. Now, let me make this remark again. Now, how many points should you choose? How many k you should choose? So, it is a critical point, because if it, so any signal will have fluctuation at different scales, right. So, my signal, let us imagine my signal velocity, one component of velocity field is like this, random. Now, given this signal, what should be, it is 1D signal. Okay. So, I want to do 1D spectral method. So, what should be my n? What will determine n? So, look at the fluctuation at the smallest scale. So, one thing is to do the Fourier transform. If I do the Fourier transform, then I will get, now you can compute energy. So, u of k mod square factor 2. Now, for different wave numbers there is energy. So, imagine that my k max is here, but my energy is going like this. Energy is not 0, but it is finite, is like this, is finite value and just decrease by half. So, do you think I did it, I mean, can I stop my k max here? Should I stop or should I not stop? So, condition is that I need to take care of fluctuation, all the fluctuation which has significant energy. Now, if my k max here there is significant energy, I expect if I go to slightly more shorter wavelength, then there will be significant energy there too. So, I should not use this k max, but I should in fact go to largest k where this energy becomes 0. 0 is 10 power minus 8, non dimensionalized, 10 power minus 6. If you miss out any signal, then there will be a problem. So, you want to resolve, this is called resolve, you want to resolve all scales. Is that fine? I mean, this is intuitive idea, and in fact, initial condition you must filter, you must use this condition, make sure that your energy, when I initial condition, first do the spectra, outside your code, and in the spectra see whether what is the k max from the spectra you can figure out, and then use your grid size accordingly. Okay, if you are using somebody else's given data, but it is possible that for the projects you are doing, you know the initial condition, right. In stability you are using some modes, and that is your initial condition, right. It may generate more modes, so you should keep n larger than what you are putting in modes, but you can choose set of Fourier modes as initial condition, or you can also use random initial condition. So I mean this is like a random signal, this one, but I will say, well, I will choose myself some signal, but my phases are random. So we will discuss that. Well, I don't know whether we have time for this, but there are ways to generate random initial signal which preserves divergence free condition. This is very important condition. Initial condition must satisfy this condition. If it does not, then there will be problems. Okay, so there's.
Can the simulation make it divergence free with time marking?
No, in fact it may get worse.
Okay. In FDM it happens that if even though if the initial condition.
No, spectral, if you don't satisfy, it may blow up. Okay. So time stepping. Now once we have the initial condition, it's an initial value problem. For every Fourier mode, we just time advance. No? So time step. So there are many schemes, Euler, RK2, RK4. So everybody knows about these schemes. No? So Runge-Kutta fourth order. There are other schemes which we don't have in our code, but I am not going to describe them anyway. So there is something like Adam-Bash fourth, but some time stepping scheme. And so there is one important point to keep in mind, is that there are two, well, there are many time scale. Turbulence is a multi-scale problem. So for every k there are two time scales. In fact, let us just write it here. U dot, well, at least two time scales. There is every k. One is nk, nonlinear term, minus nk. Another one is nu k squared uk. Pressure is roughly same order as n, but there is a force as well. So I am ignoring force coming from the force. So one time scale will come from here, right. So this is u by t is n. So I can get a time, right. So this time coming from nonlinear term. Another one is coming from viscous term. U by t is nu k squared u. So t viscous is 1 by nu k squared. Okay. These two time scale can be very different. If viscosity is small, well, I mean, you see these two can be very different, depends on wave number and so on. So one idea is, so this becomes there could be problem of stiffness. So if I mean we did in our computation for this course. So if the two time scales are different, then you have to choose smallest of the two, and that can be very expensive. So one idea is to get rid of the one of the time scale altogether, and we do some nice trick called exponential trick. So we can absorb the viscous term by change of variable. Okay, I am just telling you this one, but we have a manual of our code. You can have a look. This is very simple scheme. Okay. So no need of Crank-Nicolson for spectral method. Spectral method for in periodic box we don't need it. So so there is something called de-aliasing, which I will discuss it after some time. So I am pushing it towards the later part of today's lecture. Okay, so how do you compute the nonlinear term? Now is that clear? So we go back. So I set up my grid, I set up my initial condition, and also choose a time stepping scheme. So I am almost ready. So now each term has to be computed. right, in the right hand side. So, the pressure term is quite easy. So, somebody, well, I compute pressure from my nonlinear term and force. So, this is straightforward. My viscous term is like this way, but as I said, I absorb it with exponential trick. But in any case, if you do not absorb it, it is just straightforward, no multiplication of velocity field. Force will be also straightforward. Somebody gives you a force, but the problem is the nonlinear term. Now, it is u dot grad u. So, del j u j u I. So, in Fourier it becomes I k j u j u I. So, it becomes a convolution, right, we discussed that in the class. So, for every k, how many products the convolution has, addition and products. So, if my grid is n cube, let us I make nx, ny, nz equal to n cube. So, I will have how many here. So, this is my n of k is I k dot u q u p, or q is written as k minus p sum over p. So, how many products I have? For every p I multiply 2 velocity field, right, and how many p's I got, how many wave numbers, n cube. So, for every k I have n cube multiplication. Now, how many wave numbers I got, n cube, well, divide by factor 2 if you like, but that does not matter. And if n is large, then I have huge number, n to the power 6. Now, we do right now is routine to do 1000 cube simulations. So, that makes it 10 power 9, and 10 power 9 squared will be 10 power 18, okay, is huge. Supercomputers can't handle it. So, convolution not possible. So, there must be, well, they are not, I mean, there is a brilliant applied mathematician, Orzhov. He suggested a very clever trick. He says, do not do convolution. In fact, now everybody knows convolution is not done directly by multiplication, it is done using what? Anyone knows? Using fast Fourier transform. Okay. So, Fourier transform is the way I wrote my formula is n squared. If there are n points, then I have n multiplication. So, usual Fourier transform, the way it is written, f t, which I am going to do maybe in the next set of slides. Huh? So, f t is n squared, but again there are clever mathematicians Cooley and Tukey, so these two people, they devised a scheme where it could be done in n log n. Okay, there is a big reduction. Now, this n, well, let me call it m. If there are m points, which is n cube, m itself is n cube. So, then according to this algorithm, fast Fourier transform, it is m log m, not m squared. So, if you have 10 power 9 points, then it is big reduction. So, log of 10 power 9 is pretty small number. Okay. Anything log compared to m is small. So, it is a big reduction, and that is idea we do it with fast Fourier transform, and I will show you how it is done. So, we do not do convolution. In fact, for all image processing, signal processing, nobody does convolution, is used using fast Fourier transform. So, this was very useful trick. So, not the usual Fourier transform, that is expensive. You have to use fast Fourier transform, and I will not discuss why, how it is made fast. It is very simple idea again. All the great ideas, well, according to me, are simple ideas, and it just gives you that solution. So, is described in this picture. So, I will just go through this line. Okay. So, this is my velocity field in Fourier space. K is Fourier. Okay. Now, inverse Fourier transform. So, we define like this: the real to Fourier space is forward transform, and from Fourier to real space is inverse transform. I is inverse. So, I go down. So, if there is m points, then it is m log n. Now, if I have the velocity field in real space, I can multiply point by point, right. So, they are in fact local products. So, when we have u dot rad, so we write this as del j u j u I, keep it in real space, do not make it Fourier space. So, forget about del j right now, just product, this is real space product, and how much money, how many multiplication will it require? M, right. So, there m points, it is a local product at the point itself. So, this requires m squared, m multiplication. So, this in fact is just m, this is order, O means order, it could be the prefactor of 5. So, I got this product, then do the Fourier transform. So, how many points I got in the product? There are m points. If I do Fourier transform, how much time will it take? How many products? It is order m log m. So, I already have now the product in Fourier space. Now, I need to take the derivative. So, derivative in Fourier space is ikj. So, I multiply by ikj, that is a local product in Fourier space. So, there are k's, but I need to do either kx or ky or kz depending on which derivative I am taking. So, how many multiplication will this require? M, right, it is a local point, so order m. So, what is the complexity? This is called time complexity. How much time will it take? What is the time complexity of this algorithm? It is m log m plus m. So, log m will win over constant. Which is bigger, m log m is bigger or m is bigger? Which one is bigger? M log m is bigger. No, log m is small but not too small, it is bigger than 1, right, I mean 10 power 9. So, is log to the base 2, right, okay, this is base 2. So, this is basically 9 log 10 base 2, which is around 3. So, 27, 28 of that number. So, the whole algorithm is m log m, not m squared. So, that is how we compute the nonlinear term. We do not do convolution, and this is where fast Fourier transform comes into play. So, in our lab we have developed a scheme called a library called fast Fourier transform Kanpur. Okay, Anando is the developer. So, this is what we use. It is a parallel library, and so that is used for this computation.
The multiplication of ui with uj.
Mm-hmm.
What do you mean by local product? Why is it m? I didn't understand that.
Okay. So, let us do in 1D. Okay. So, 1D, what is, so ux x ux x. So, x equal to 0 I multiply, x equal to 1 I multiply again at the velocity field at that point. So, if you have n points, how many multiplication do I need? N, right. In 3D same thing, every point I have a velocity field at that point and I get a product. Now, this ui uj is a tensor. So, you have to compute all the components. So, you have ux ux, ux ui, ux uz. So, how many are there? There are 6. It is a symmetric tensor. So, you have to compute, but it is a local velocity field.
So, it's basically 6m.
6m. Okay. Now, once you are done with the nonlinear term, you are all set. So, I can time it once. Now, I am not doing all that details, but Euler scheme, it will be just straightforward. So, Euler scheme will be, so we have d by dt of velocity field, everything is right hand side, I put it there including the viscous term, and given initial velocity I can get uk t plus delta t is uk t plus RHS times delta t. Okay. So, RHS is function of k, but is done for all k's. Now, by the nonlinear term is computed for all k in one shot. You need to store it in arrays, but it is not that for every k I do it one at a time. I just when I am here, it is done for all wave numbers. And once you have the nonlinear term, you also have to compute pressure. So, nonlinear term is used for computing pressure. Okay. Is that clear? So, this is how spectral method is written. So, this is a sketch. If you are courageous enough, you write one for yourself, but we will give you a code which you can use. Okay. Now, what about energy transfer? So, I defined all of it. So, the last lecture is the most important lecture, where I defined flux, shell to shell. So, we need all those information for my future discussion. So, from any region A to any region B. So, how do I compute? So, by the way, any region A and region B, one thing which we will do it for the next, we will need it for the next class, is energy coming out of the modes inside the sphere to the mode outside the sphere. So, this will be region A and outside will be region B. Okay. Now, this formula you remember. So, this is receiver wave number, this is a mediator, giver and receiver. Okay. So, we have convolution here as well, P is k equal to P plus Q, but remember P is a giver, lies in region A, and k is a receiver, lies in region B. Okay. So, now giver is not all the wave numbers, giver is only belongs to region A. So, I construct a new velocity field, UA, which is uk if k belongs to A. Actually, I should not put this one. If k belongs to A, not mod. Okay. If k is inside A, and 0 if k does not belong. So, it is a truncated velocity field. So, UA is the velocity field of this region. In real space, what will it correspond to? In real space, it corresponds to large scale flow. Is in electrical engineering is called filtered velocity field. So, you filter small scale, only keep large. So, this is like filtering, only the rich people are invited for this, So, this is a filter, you applied a filter. Now, UB is other region. So, we do the same thing. Okay. So, k belonging to B. So, this is region A and now we have region B. So, this will be region B. So, I keep the velocity field non-zero only in that region. So, U and UB. Now, after this is quite easy. Now, this is again a convolution. So, you do not do the convolution. Convolution will be very, very expensive. So, we use idea of fast Fourier transform again, and the idea is the following. So, I rewrite the above equation like this. So, kj uj. So, q is k minus p. Okay. So, this one k, this one is written here, kj this one. This whole thing is written here. Can you see that? A giver is ui of A. Now, I am doing dot product. So, it is a tensor notation. So, I B complex conjugate and like this. So, this sum P sum is inside. So, what is this? This one? No, in terms of what I described some time back in my. So, this is uj ui k minus p a is a nonlinear term, right, and kj, but it is not full nonlinear term constructed with full velocity field, nonlinear term constructed by u of a is exactly same, it is u dot grad u, but u dot grad u, but this u is a, ua. Everybody is happy with this? So, I can use the same old algorithm which I did in the last slide and just use that function. So, this is a nonlinear term. So, how will I do it? I go to real space, multiply, Fourier transform and then multiply by kj. Okay. So, this is how I compute, and by the way this is called pseudo spectral. Why is it called pseudo spectral? Because I am going to real space. So, it is not fully spectral, no, you are cheating in between, you are not solving everything in Fourier space, you are going to real space, doing something and coming back, okay, and that is why it is called pseudo spectral. Once I compute the n linear term, which is n of k, p is summed, so it is only function of k, then I multiply by u of k and sum over k's, but I do not sum over all velocity field, I sum over only the b part of the velocity field, and once I do this, then I get this t which is desired. So, this is that energy transfer from A to B. So, by notation I should say that. So, top is a giver and bottom is a receiver, and the first letter is what field. Now, I am only using velocity field, but sometime later we will also use magnetic field. So, this may change to B for magnetic field, and this is the region A, B. So, to compute flux, I just have to put region A is inside the sphere, B is outside the sphere, and they will give me the flux. So, this is how we compute in our simulations. Now, there is another way which is also used. So, let me just tell you how is it done. So, this formula I derived in the last class. Now, it is quite easy to see intuitively. What is the flux? So, is energy coming out by nonlinear interaction. So, this is flux. Now, so the question is how energy can change inside the sphere. Energy can change inside the sphere by many ways, several ways actually, I will not say many ways. One thing is I am losing by viscosity. I think I described that in the last class. No? So, it loses by viscosity, this is a viscous term. So, d by dt of EU inside the sphere is minus viscous term, minus d. Now, I just spent, or I lose by nonlinear interaction, by exchange. It is not losing by dissipation, but I am giving loan or I am doing something, you know. So, this is like interacting with people. So, that is flux pi. This can be positive or negative. And third is I get from some external force. So, that we put a plus sign. So, Fu F this math cal flux minus d, there is a minus sign, flux is going out. So, if flux is positive, then I am losing. Now, this is written here above. So, how can I compute flux? I can compute the time rate of change of energy of the sphere at two different times, you know, just take it time t, then time t plus delta t, subtract, divide by Newton, you know, just Newton. I can compute these as well. Somebody is forcing inside the sphere, and that can give you this one, and I can compute this. So, all the 3 terms in the right hand side can be computed. To compute the time derivative, I need 2 different times, but all 3 terms can be computed. Once I compute all 3 terms, I can just add, subtract, I can get flux. Okay. So, this is another way to compute Kolmogorov flux. This is called Kolmogorov flux, which I am going to come to it in the next class. We will discuss that. In fact, turbulence will start only tomorrow.
But its accuracy depends on dt, na?
Yes. Also, it depends on, well, yeah, true. So, you should keep dt small. Okay. So, this is how we compute. So, basically, we can solve our Navier-Stokes equation. We can also compute various energy transfers. Now, we can generalize it to more complex fields like convection, which some of you, I mean, we did in the class. So, we have additional field temperature. So, we have another PD, partial differential equation, equal to something. This is a nonlinear term, minus 0 at t. But you can solve exactly the same way. Compute the nonlinear term by pseudospectral method. Viscous term will be a diffusion term. So, follow the same scheme. For MHD, there is one more equation. For magnetic field, you can solve it. If you have magnetoconvection, then we have 3 fields: velocity, magnetic, and temperature. But no problem, we can just solve this using same method. So, having more equation in more terms, method is the same, but just you have to take care of more variables, more nonlinear term, and so on. So, I just want to tell you maybe one slide, but we will get back to it a bit later. So, there is a code Tarang developed in our lab. So, it is object oriented. Why object oriented? Because we have one code to solve, I will not say everything, that is too much, but fluid, MHD, convection, rotating flows. So, this is a general PD solver, PD spectral solver. Okay. So, since it is general, I can plug in more variables, plug in more nonlinear terms, and it does it. It's parallel means I can use many computers to solve this equation. It's faster, otherwise this will take too long, impossible in fact if you do not use parallel, and it computes energy transfer. This is advantage of this solver. This is not computed by everyone. I mean, this is unique to our lab, that we compute this energy transfers, and it gives you a lot of insights. Okay, so I think this is about my discussion on spectral solver, except aliasing, okay, and FFT. So, I will do it in next set of slides. There will be a small one, but we will do it after this. Thank you.